Am I audible, Suresh?
Yes.
Okay, we'll start the session. Okay. Good afternoon to everyone, to all the participants. So, welcome to the last day, last session of this short term course on emerging technologies and processing of advanced materials and its characterization. So, this session would be handled by Dr. G. Suresh Kumar, Assistant Professor from IIT Hyderabad. Dr. Suresh Kumar pursued his PhD in Technical University Darmstadt and Karlsruhe Institute of Technology, Germany. He did his master's in Metallurgical and Materials Engineering Department at IIT Madras and received that fellowship during his master's. He also worked as a research fellow in the Zepler Institute at the University of Southampton, UK, and as a postdoctoral research associate in the Department of Chemistry at the University of Manchester, UK. His research interest includes printed electronics, oxide semiconductors, electrolyte gating, organic electronics, flexible electronics, gas sensors, and memistors. Now, I warmly welcome Dr. Suresh Kumar. I request Dr. Suresh Kumar to kindly take over the session. Thank you.
Okay. Thank you, Mahesh, for the kind introduction. I hope most of them are students. So I would like to have more of interaction session rather than a simple talk.
Yeah,
so
sure.
I hope students respond to the questions.
Yes, they are. Right now, there are first year electronic students are also present. So
Okay,
it will be very useful for them.
right. So I will share my screen. Aren't I screen? So Mahesh, can you see my slides?
Yes, yeah, exactly.
Okay. Okay, it is here. Fine. Thank you, Mahesh, for the kind introduction and for the opportunity. Welcome you all to my talk today. Today I will discuss about printing electronic materials and devices. So are simply nothing but printed electronics. So what you can see here in this image, for example, in the center, we have a printer. It's a roll-to-roll printer that is printing actually different functional materials. Functional in the sense they are, let's say, electrically conducting or non-conducting materials, which have either insulating or conducting or semiconducting property, right? And then you can print on different surfaces, let's say, including the flexible plastic, paper, glass, any other substrate that you can think of. You can print on variety of surfaces, even on 3D surfaces you can print, right? And then you can make different electronic devices, for example, transistors, diodes, capacitors, resistors, and so on. So these devices can be used in variety of applications. I'm just showing you some examples here. For example, you can have an RFID tag. RFID tag is nothing but radio frequency identification tag, which can be attached to a product, and the product can be tracked within the detector range. So it can have several advantages, let's say in the supermarket, or also it can prevent the theft, and it can also save your time while doing the shopping. And you can also make smart packaging devices. Smart packaging, let's say you can have a sensor that can detect whether the food is still fresh or whether it is spoiled, and it can give you a message that the food is spoiled, you don't need to eat, right? And also you can have smart textiles. Smart textiles in the sense you can have sensor in the textile that can detect body temperature, stress level, or the moisture level, and it can alert you, your doctor when you are ill, and so on. So also you can have displays and Internet of Things. So several applications are possible using this printed electronics concept. So before I go into the topic, I would like to ask you one simple question. I think many students are here, so I would like to know how computers are getting smaller and smaller with time.
Participants can unmute yourself and then answer the questions, or you can get the questions clarified.
You know, right? Computers, let's say, who is the father of the computer? Does anyone know?
Charles Babbage.
Charles Babbage. Yes, yes, great. Okay. So the first computer you can see in the first image, for example, it is actually an entire hall, right? It's a very huge one. To do simple arithmetic or logic operations, you need to have a large number of devices. But later on, let's say Alan Turing and other scientists invented, and then the computer is the modern one. You can see the size is getting reduced, and the modern one is further reduced. I think in the future we can have even in a palm or just in hand. You can have a small computer, right? So my question is how they are becoming smaller. What is changing? Their performance is in fact improving, right, with time.
Micro and nanotechnology.
Yes, that is one. Yes. Any other thoughts?
More and more involvement of scientists in the field of nanotechnology so that the computer processing power increases.
Yeah, that is it. That is evolution process. But there is one key component actually that is replaced. So that's why it is becoming smaller and smaller.
Whites are reduced. Whites and optical surface is reduced.
No, I think.
Okay, you are getting closer and closer, but I just remind you, you know something called vacuum tube?
Yes, sir.
Yes, sir.
Ah.
That for CPU they use.
Yes. So initially it was actually vacuum tubes which were used in computers, right? So vacuum tubes, what it has a, let's say, glass jar filled with vacuum, and you have a cathode. This is a cathode and a control grid and an anode. So thermionic emission, let's say when you heat the filament actually releases the electron. Okay, that is the thermionic emission. These electrons travel from cathode to anode through the grid. Okay, you can control the charge carrier flow, the electron flow from cathode to anode. That way you can tune the electrical current in the device. So what is the function of these vacuum tubes? They are actually having an electronic switch behavior, right? They can amplify the power supply. Also, they can switch off. So like your regular switch where you can, let's say, switch on and off your fan, here you can electronically switch on and off. You can amplify the power supply, right? So this kind of vacuum tubes initially were used in the computers. These vacuum tubes were very bulky and inefficient, and they are also not safe, right? They are expensive as well. So these vacuum tubes, although of course, initial days, they used heavily in all, let's say, radios, televisions, and computers and many other electronic devices. But during, let's say, after the invention of one more device called transistor, I think this most of you heard, right? Transistor. Transistor is nothing but a three-terminal device where you can have, let's say, a source, drain, gate electrode, and you have an insulator here. So the charge carriers that are flowing between the source and drain are controlled by applying the potential at the gate electrode, right? So it is having the similar function, but this is you can operate this in air, and also it is very stable, efficient, and the size is very smaller. And most of you know, for example, Moore's law, right? For every 18 months or 2 years, the computers, the transistor size is getting, let's say, half, or nearly reducing to half of that one. So by that concept, the transistor size is reducing smaller and smaller, and you are replacing these transistors, let's say, in the computers. That's why the computer size is getting smaller and smaller with time. Okay, so today I will talk about these transistors. So this is the outline of my talk. So I will discuss about, let's say, what is matter and what are different states of matter, and then how the energy bands are formed in a matter, then how this semiconducting materials are have the band gap, and how these are used in a transistor, and what are different types of transistors, or what are different types of applications, then how to prepare the transistors, and then are there any inexpensive or simple way to prepare the transistors, for example, the printing process. And then I will discuss about different printed electronic devices. So this is the outline of my talk. So I would like to ask you again here, matter we know, right? There are three states of matter: solid, liquid, and gas. I'm just showing the figure. So what is the difference between these three? Anyone can unmute
More
and
clear
answer.
spaces.
Molecular
Arrangement of
attraction.
particles. Arrangement of particles.
Yes, arrangement of atoms, right? So the atoms are arranged in a different way. For example, if you take solid, they're very closely packed, right? In case of liquid, they're not that close. In case of gas, they are very far apart. So that changes their structure, their properties, and entire properties of material, right? So what the atoms consist of, everyone knows it has electrons, protons, neutrons, right? Electrons are revolving around the nucleus, right? But when you have individual atoms, these energy levels are discrete, right? So if you have 1s electron, you have, let's say, 2 electrons in the 1s state. Then you can have 2s, 2p, 3s, 3p. So these are very discrete for an individual atom. But what happens when we bring these atoms together? Let's say if I bring 12 atoms together, for example, for carbon atom, right? So if I bring the 12 atoms together, what is exactly happening? So, you know, Pauli's exclusion principle? Can anyone tell Pauli's exclusion principle? Anyone know Pauli's exclusion principle? Just to recall.
No two atoms of same, sir.
Yeah, go ahead.
No two electrons of same atom have identical quantum number.
Yes, no two electrons can have identical quantum numbers, right? That is a simple
No
definition
two
of.
identical.
Yeah. So even if you have, let's say, the principal quantum number n, then you have azimuthal quantum number, then you have magnetic quantum number, then you have spin quantum number, right? So even if the first three are same, the last one, the spin quantum number, is different. You can have plus half and minus half. But if you take individual atoms, they are discrete. But if you take multiple atoms and let's say forming a bond, what happens is you have to have same energy level, 1s, 2s, 2p, but you cannot violate Pauli's exclusion principle, right? So what happens is that the 1s electronic state now will split. If there are 12 atoms, now it will split into 12 electronic state. Similarly, the 2s electronic state also will split into 12 electronic state, right? So that it doesn't violate the Pauli's exclusion principle. So you can have individual electronic state when the atoms are far apart, but when they are coming closer and closer. So here the graph is showing interatomic separation versus the energy band, energy levels, right? So when they are in the gaseous state, they are completely discrete. When they are liquid state, they are coming closer and closer. But when they are solid state, you can see these energy levels are now splitting into multiple energy states. Imagine in a solid you can have let's say billions of atoms, right? So when you have such a huge number of atoms, what happens is you can have huge number of splitting of energy levels. So now you can see again the interatomic separation versus the energy band. But here what we are showing is like a solid, but actually it's not solid. They're completely discrete energy levels, okay? But they're very, very close. So that's why at equilibrium atomic spacing, you consider these energy levels as a band, okay? So the lower one is called valency band and the upper one is called the conduction band. So there is a gap between these two bands that is called energy band gap. So now we understood that there are discrete energy levels, but when the atoms are coming closer and closer, the atomic orbitals or the electronic states are splitting, and that is leading to the energy band structure, right? So what are different kinds of materials? We know, right? There are different kinds of metals, semiconductors, and insulators. In case of metals, so the valency band and conduction band either overlap or you can have half-filled valency band. So an example, if you take sodium, what is the atomic number of sodium? Anyone know what is the atomic number of sodium?
11.
11.
Yes, 11. So what is the valence state? What is the valence state of sodium?
1.
1.
Yes, it's 1, right? So that means the s orbital is half filled. So you can see this valence band is now half filled and the half is empty. So the electron can now easily jump from this level to the next level very easily. Even at room temperature, it can jump. That's why the metals are very easily conducting materials. Okay. Or in other case, you can have overlap of bands. There also you can have an empty band immediately above the filled band, so the electrons can jump. Whereas in case of semiconductors, that's not the case. So there is a gap between the valence band and the conduction band. So this is called the band gap. But this gap is not very high. For example, if you take silicon, the band gap is 1.1 electron volt, right? So the gap is in fact very small. So if you, let's say, supply some amount of electrical energy, the electron from the valence band to conduction band can jump. Okay, and this conduction band electron can lead to conductivity. Whereas in case of insulators, the energy band gap is very huge, right? So you need huge amount of energy to excite the electron from the valence band to conduction band. So that's why the conductivity is very poor in case of insulators. The conductivity is medium, and the metals are very high conducting in nature. So this is the conductivity graph that is showing electrical conductivity of different materials. The metals, you can have very huge conductivity, 10 power 4 to 10 power 8 Siemens per centimeter. Whereas semiconductors, you can have intermediate range of conductivity. In case of, let's say, insulators, like ceramics or non-conducting polymers, you can have very low conductivity, right? So these materials have different electrical conductivity, and we can actually tune the semiconductor conductivity. Whereas in case of metals and ceramics and polymers, the tuning of conductivity is not that easy. You can still tune it, but it's not that easy. In case of semiconductors, you can tune the conductivity because of the band gap that they have, the smaller band gap they have. Okay. So as an example, we know the famous silicon, right? Silicon, what is the valency of silicon?
4.
4, right? So silicon can form covalent bond with 4 other silicon atoms, right? If you take, for example, one silicon atom here, it can form bond with silicon, this one, this one, this one, right? It is sharing the electron and forming the covalent bond. But at room temperature, the thermal energy is enough to break some of the bonds and excite these electrons, right? So what happens is these electron now free, it becomes free from the bond, and it can actually move under the influence of electric field. And also the hole is nothing but missing of our empty space of electron. So you can have 2 charge carriers. One is the free electron, other one is the hole charge carrier. So under the influence of electric field, these both charge carriers move and leads to conductivity, right? So the conductivity is coming from both electrons and hole charge carriers in case of intrinsic semiconductors. Intrinsic, I mean, we are not doping with any other elements. Intrinsically, they are having semiconducting in nature. You can also have an n-type semiconductor. N-type, for example, if I dope with phosphorus, it is pentavalency, right? So in case of phosphorus, it can donate an extra electron. For silicon, we just need 4, but phosphorus is donating 5, right? So that means this electron is not participating in the bond, and this is free from the bond. So under the influence of electric field, this free electron can now move. Okay, so that leads to conductivity. So since the majority charge carriers are now here free electrons, that's why it is called n-type silicon. So just understand here, the number of protons and number of electrons are equal. So the material itself is not charged, but in the material you have free electrons which are not forming in the bond, and these electrons move, right? So since the electron is a negative charge carrier, that's why it is called an n-type semiconductor. But if you take a p-type semiconductor, where you can dope the silicon with boron, right? Boron has valency of 3. So when you dope the silicon with boron, so it is having a, let's say, a hole, because the electron is missing here. So this hole now can move under the influence of electric field from one place to other place. So the movement of the whole charge carriers now leads to conductivity. Okay, so here the majority charge carriers are holes. That's why it is called p-type semiconductor. Okay, so how we can use these semiconductors in a transistors? If you take, let's say, simple a conductor, 2 conductors which are separated and then connected by a semiconductor, and then you have another non-conductor, and on top of that you have a conductor. So what happens is you are forming a capacitor. This is the conductor and this is a semiconductor. So there are charge carriers in the semiconductors, charge carriers in the conductor, right? So when you have a potential, that actually leads to accumulation of, let's say, positive charge carriers here and the negative charge carriers here. And then when you create the potential difference between these 2 conductors, the charge carriers can now flow from one conductor to other conductors. Okay, so by applying the electric field, you are controlling the charge carrier flow in the semiconductor. Okay, so that way you are tuning the conductivity of a semiconductor. So the transistor is nothing but a three-terminal device. For example, this is the gate electrode, source, drain, and then you have a non-conductor and you have a semiconductor. So this is a simple structure of a semiconductor. Of course, there are different structures of semiconductor, but I'm just showing you one. So semiconductors can be used in a transistors. In a transistor, you can control the charge carrier flow. That can lead to controlling the conductivity, which can be used in different electronic devices, right? So these transistors actually replace the vacuum tubes, as I mentioned before, and they also have low power consumption, and they're extremely small in size compared to, let's say, if you take the nanometer technology. Currently, we have 3 nanometer technology as well. So they are extremely small in size. They are very high speed. High speed means you can tune the charge carrier flow in gigahertz frequency range, right? And also you can see the graph here. This is the current versus voltage. It shows that the current is actually tuning from, let's say, significantly low current to significantly high current. You can have orders of magnitude change in the current. You can have 10 power 7, 10 power 8 orders of magnitude change in the current for the transistors. So such a transistor can be used in electronic devices. So this transistor was actually invented by 3 scientists at Bell Laboratories in USA. So they are John Badin, William Shockley, and Walter Brattain at Bell Labs in 1940. They invented the transistor. So the first transistor actually is very bulky, but actually that is the first invention. They use the point contact transistor, where they have used the germanium. In case of germanium, they could control the charge carrier flow using the bipolar junction transistor concept, and they could generate the current. They got, of course, Nobel Prize in 1956. Currently Intel is developing the transistor. Of course, there are other companies as well, Taiwan Semiconductor Technology, Intel, and also Samsung. So all global foundries, they are all developing transistors. This is just one I'm showing you. 14 nanometer technology. Currently, they have 15 million transistors. But the very recent one, there is 3 nanometer technology. 3 nanometer technology has now 300 million transistors. So imagine how many transistors are there in a square millimeter, and how quickly you can control the charge carrier flow and the current, and that will lead to the reduction in the electronic devices. So of course, these transistors have several applications in electronic circuits, in mobiles, smartphones, displays, and also in the latest sensors as well. These transistors are widely used. So just to summarize the first part of the talk, so we discussed about the matter and how the discrete energy levels are there, and how we are getting the energy bands for different materials, metals, semiconductors, and insulators, and how we can control the charge carrier flow in case of semiconductors, both intrinsic and extrinsic semiconductors, and then how we can make how the transistor is, let's say, developed at Bell Laboratories, right? So that is a summary. If any of you have questions, you can ask me now. Feel free completely and ask me any question you have. I will tell you.
Sir, nowadays I have heard that sir, chips have been inserted into human brains so that it can give commands to other devices, sir. Sir, in that also transistor like nanomaterials are used?
Yes. This is called the latest neuromorphic computing, right? So there the chips are inserted into the brain. There also they use the same silicon-based transistors, but these chips have to be biocompatible. At least the inner part has to be biocompatible. So people are working also on alternative materials, but currently silicon-based transistors are used in chips.
Okay, sir.
Is that clear?
Yes, sir.
Okay. Any other questions? Completely feel free. You can ask any question. If I know, I definitely tell you answer.
Sir, sir, again, if anyone want to select this field as his career, so sir, what are the things you will suggest him to do?
Of course, you need to do coursework, right? You need to do electronic device coursework, physics of semiconductor devices coursework. After that, you can work on a project. You can, let's say, choose different institutes and work on electronic device concept. Later, you can move to that career.
Sir, sir, are there any setbacks for this transistors?
There are. I mean, currently the technology is actually near to the Moore's law. I mean, they are trying to find alternative technologies. This 3 nanometer is actually kind of limit to the technology. So they are working on quantum computing and also nanowire transistors and nano quantum dot transistors. So there are different transistor devices. They're still working on it because they are leading to high power consumption when the size is lower and lower.
Okay, sir.
Okay. Any other questions? Okay, I assume you understood, although some of you might feel shy, but you can ask me the questions later on as well. So now we move on to the preparation concept. So until now we understood what are different materials, transistors. So now how to prepare the transistors. In case of conventional transistors, I mean silicon-based transistors, there are actually many steps. There are more than 20-30 steps. I'm just showing you the few steps where you have to take, let's say, silicon wafer. On that wafer you have to do lithography process and deposit, let's say, the high-K dielectric material. Then you have to deposit the gate material. Then you have to deposit the n-type semiconducting material. Then you have to deposit other materials and I mean the contact materials, and then you have to remove the contact pads as well at the end. So there are multiple steps involved in case of preparation of transistors, because of course it is very nanometer technology. I mean very small in size. So of course you need this kind of lithography and high vacuum based techniques. They are expensive as well, but you need this kind of technologies to prepare. But not all kinds of transistors are required. For example, if I want to use for a simple sensor, why I need to have expensive transistor? Can I make the same transistor or similar transistor using some other technique, so that I can use these transistors in low-end applications? For example, simple sensor that can sense glucose level in the blood, or let's say the temperature sensor. Can I use some kind of transistor which can be prepared by a simple method? So people have tried different methods, and people have come up with a new technique. In fact, the technique itself is not new, but for the transistor, it is new. That is called printing technique. Printing is nothing but depositing, let's say you take some functional link and deposit on different surfaces to fabricate different devices. So printing technique itself was the modern printing technique itself was considered to be invented by Johannes Gutenberg. He was German. So during 15th century, he invented this movable printing press. During that time, it has actually the revolution in the society, because it could create the communication between different parts of the world. They could print Bible and they could communicate the Christianity, and also of course there are many other ideas that are also communicated using the printed books. So it is actually the revolution during that time. In fact, Time Life magazine considered this as actually the second most the first most the most important invention of second millennium. But of course, later on, we also have the internet, which is also the communication part, and also we have widely accessing nowadays. Of course, we are talking also through the internet. And the current one is actually the printed electronics. So the combination of the electronics and the printing concept. So that is called the printed electronics. It is creating actually new kind of applications. You can have, as someone said, you can have chips in the brain. You can have sensors. You can have printed sensors on a surface. You can have printed solar cells on a building. So you can have 3D printed electronics, 3D printed sensors. So you can have wide variety of flexible electronics and also Internet of Things. So many of applications are possible using this printed electronic concept. So this printed electronic concept, as I told, we have to make functional inks, and that ink you can deposit, let's say, different techniques. So one technique is inkjet printer. Inkjet printer has, let's say, cartridge where you can fill the ink, and the ink is actually dispersed through this cartridge onto different surfaces to fabricate the devices. So if I just want to compare the printed electronic concept with conventional I mean silicon-based electronics. So the printed electronics concept is actually the low cost, because it is completely non-vacuum based techniques, and they are very cheap techniques, and you can print at room temperature and also at any lab. You don't need ultra high clean room labs. Whereas conventional silicon-based electronics, you need actually ultra high clean room labs. So if you go to labs, you might see that people are completely wearing mask, they are wearing apron, they are completely covered. They can't breathe very easily, but still they have to work. So that kind of ultra clean labs are required, and they are very expensive as well. But the advantage of conventional electronics, they have high integration density. As I told before, you can have 300 million transistors in a square millimeter chip. Also, they have short switching times. These are the advantages. In case of printed electronics, there are disadvantages, but the integration density is low because the printing electronics is concept itself is not a high resolution one, it is a low resolution one. So the density is very, very low, and they have long switching times. These are the disadvantages. But the advantages are large areas. You can print millions of meters or square meters or kilometers. You can print, for example, how you are printing a newspaper, right? You are printing a roll-to-roll printing on a square millimeter. You can print square kilometers as well. So such kind of large area you can print using printed electronics concept, and the fabrication is also very simple, and you can have flexible electronics concept as well. So these are the advantages. Whereas the disadvantage for the high cost one is, or the conventional electronics is, they are sophisticated, as I mentioned before, and they are rigid on silicon wafer, and they're of course small in size, but they are very costly, right? So if I compare the printed electronics, these are complementary to the conventional electronics. Printed electronics can be used in low cost and low end applications. So that is the complementary compared to conventional electronics. So how to print? So to print, actually, you need to have an ink. Okay. So to prepare the ink, you need to make a nanoparticle or nanopowder that can be dispersed in water or other solvent using surfactant. And after the dispersion, you can have either stable or unstable ink. So stable, I mean the particles that do not settle down at the bottom. Okay, so they're completely dispersed. So dispersed and dissolution, there is a difference. Just to understand, dispersion means they are not soluble in water. Okay, they just stay as nanoparticles, but they're separated because of the surfactant. Right? If you don't have surfactant, they will completely coalesce and become a solid or sediment at the bottom. For example, this ink, you can see the ink is completely settled down. You can have transparent one. So this is not good one. This is not stable. Whereas this ink is stable. So you need to have a stable ink. So for that, you need to choose the nanoparticle size and the right surfactant. So that you can get a stable ink. So this ink, as I said before, this is the dispersed ink. This you can print using, let's say, inkjet printing concept, where you can have a nozzle and a piezoelectric transducer. So what happens is, when you apply the voltage to the piezoelectric transducer, it will, let's say, create the compressive pressure wave. So that compressive pressure wave will eject the droplet. Okay, this is a droplet with nanoparticle and surfactant. These are the surfactants. So you can print on a substrate. You can make the thin film in that fashion. And of course, you can remove these surfactants by either heating or by treating with the laser or UV light or any other method that can remove the surfactant molecules, so that you can have a conducting particle. So just understand here. So here the particles have to be in contact, right? Because it is a thin film. The thin film has to be continuous, and particle have to be continuous and contact, so the electron can transport from one particle to the other particle. So that is the reason we need to remove the surfactant. So just understand here that we need a stable ink, and the stable ink can be printed by a printing technique. And after that, you can remove the surfactant. Of course, there is another ink as well, where you can have a salt which is dissolved in a solvent. And in that case, you have to heat the solvent, the whole printed film, so that you can decompose the precursor into semiconducting material. So I will discuss that one in the coming slides. So I have used, of course, this is my PhD work. During my PhD work, I have used oxide semiconductors and electrolyte gating concept. You might wonder why I have used oxide semiconductors. Why not silicon-based semiconductors? Does anyone know what is the disadvantage with silicon? Do you know the concept of oxidation? Anyone know what is oxidation? Okay. Oxidation, let's say you take silicon, for example. Silicon is actually very reactive in air. So it reacts with
Rust.
oxygen. Yeah, go ahead. Someone wants to say something?
Loss of electrons. They are typing in the chat box. So,
Okay, fine. Yeah, of course, oxidation is loss of electrons, true. And what happens is, for example, silicon is becoming silicon dioxide, right? Si plus O2 gives SiO2. So at room temperature, silicon actually oxidizes. So that's why you can't use silicon in case of printed electronics. So you have to use alternative materials. Alternative materials are, let's say, oxide semiconductors, also organic semiconductors. Of course, there are other semiconductors as well, like graphene. Also, you have 2D metals like molybdenum disulfide. You can have carbon nanotubes. You can have fluorines as well. Variety of materials are there. But you have to choose a compatible material with printing technique. Oxides are already oxidized, right? So for example, if I take indium oxide is In2O3. It is already oxidized, but it is semiconducting in nature because it has oxygen vacancies. These oxygen vacancies are donating the electrons. These electrons move under the influence of electric field. So that's why I have used oxide semiconductors during my PhD work. So the two important materials in case of transistors are, of course, source drain gate electrodes are metals, which are, let's say, you can use any metal, either aluminum or gold or copper or many other materials are used. But in case of channel or semiconductor materials, you have to choose a particular semiconductor which is suitable for printing. So that's why I have used oxide. And next one is dielectric. Dielectric is nothing but the insulator. It has to form a capacitive nature. It has to be capacitive in nature. It should not allow the electron flow. Okay, so I have used electrolyte as a dielectric material. What is the advantage of electrolyte is, so when it comes to contact with a metal, a conducting material, so this is the electrolyte part, this is the metal part. So what happens is, it will accumulate the charge carriers from the metal. Let's say the electron are accumulated from the metal. In case of electrolyte, you accumulate the opposite charge here, that is the plus. So in case of electrolyte, you accumulate the opposite ions. So that forms a capacitive in nature. So you have a capacitor, the parallel plate capacitor. So this parallel plate capacitor is having very small distance, approximately around 1 nanometer. So such a small distance will give you very high capacitance. C is inversely proportional to distance between the charge carriers, right? So very high capacitance, for example, 10 microfarads per centimeter square, will lead to low operating voltages. So that's why I used electrolyte as the gating material and oxide semiconductors as the semiconducting material. So then, as I mentioned before, you have to use different inks. I have used the precursor as one ink. Precursor is nothing but, let's say, you take indium salt, dissolve in a solvent, and this can be heated to high temperature so that this, for example, indium chloride will decompose to indium oxide at high temperature. And then you can have nanoparticle films as well. So in that case, you have to make nanoparticles. Already you have to make indium oxide nanoparticles, which you can disperse in water, for example, using a surfactant, which can be printed at room temperature. But the nanoparticle surface has surfactants. These surfactants we have to remove. So to remove the surfactant, I have used laser curing techniques during my work. So now comes to the fabrication steps. So first of all, I have taken a substrate, right? Either glass or plastic substrate. On the substrate, we did lithography, deposited the electrode materials, followed by deposition of either precursor ink or nanoparticle ink, followed by annealing for the precursor, because the precursor has to decompose to, let's say, indium oxide. And in case of nanoparticles, photonic curing techniques are used so that we can remove the surfactant and improve the conductivity between the particles, right? So finally, printing the electrolyte. So this is the device structure. You may wonder, sir, the device structure looks different, completely what I have shown before. Yes, there are different kinds of transistor devices. So this is called in-plane transistors, where you have source, drain, gate are in the same plane. Okay, they are in the same plane. They are not top gate or they are not bottom gate. They are in the same plane, but you can connect the source drain using a semiconductor, and you can connect the semiconductor and the gate material using the electrolyte. Okay, that forms the capacitor, and the source drain actually is connecting the semiconductor where you can tune the charge carrier flow. So this is called in-plane transistor, and this is electrolyte gated transistor using oxide semiconductors and electrolyte gating concept. Of course, before I show you the electrical characterization, I just want to show you the structural characterization. So XRD, does anyone know what is XRD? X-ray diffraction. Does anyone know X-ray diffraction? How it works, X-ray diffraction, and what kind of information do you get from X-ray diffraction?
Probably these.
Sir, X-ray powder diffraction.
What is the concept of X-ray powder diffraction? Anyone know?
Sir, it is used for phase identification of crystalline or
Yes.
materials.
Yes. So you can use for phase identification of crystalline materials. Do you know how it happens? How the identification happens? What happens is X-rays having actually very small wavelength, around 0.7 angstrom to 1.5 angstrom, right? So this is actually almost equal to interatomic spacing. So when the electromagnetic wave interact with atoms, it actually have diffraction phenomena. It creates the diffraction phenomena. Okay. So when you have the constructive interference, that leads to peaks. Okay, that's what you see in the XRD pattern. So this is the intensity versus angle. So these peaks belongs to the crystalline nature of the material. So that way you can identify whether the material is crystalline nature or amorphous nature, and also what kind of phase are present in that material. So I have done XRD to understand what kind of phase are present in the films that the films that I printed and heated at high temperature. I heated at 300 and 400 degrees centigrade. At 300 degrees centigrade, the film has indium oxide, but it also has a secondary phase that is called indium oxychloride, which is detrimental, which I don't want. So then I heat it to high temperature, let's say 400 degrees centigrade. Then the indium oxychloride is completely converted to indium oxide. So this time we don't have any secondary phase and it is pure indium oxide. This is what actually we want. Indium oxide is having a semiconducting nature. So we need a pure indium oxide film. So we need around 400 degrees centigrade to decompose the printed precursor film. So then I did the SEM and AFM analysis. Again, I want to ask you, not testing, just so that we can recall, what is SEM? Does anyone know what is SEM?
Scanning electron microscopy.
Yes. What is the principle of a scanning electron microscopy? And what kind of, yeah, go ahead.
We can determine the composition, grain size.
Yes, we can determine the grain size. We can see the morphology. Of course, if you do EDS, we can also get the composition. I mean, not composition, exactly, elemental analysis. Now the question is, what is the principle of SEM?
Backscatter electron.
You have backscattered electron and secondary electron. But actually what happens is, you can have a tungsten filament or even have a field emission gun, thermionic emission gun or field emission gun, right? In case of thermionic emission gun, you have, let's say, tungsten filament, right? So what happens is, when you heat the tungsten, at the tip of the tungsten, you can release the electron. Okay, so these electrons now travel in the vacuum through the electromagnetic lens and interact with the sample. Okay, these interacted electron will be detected by the detector. So when the electrons actually interact, they carry the information or the morphology of the films or the particles. So backscattered electrons are nothing but elastic scattering electrons, whereas the secondary electrons are actually coming from the top surface, 5 to 50 nanometers of top surface. They actually lose lose energy. So they are called inelastic scattered electrons. So you can get different information from backscattered. For example, phase contrast. In case of a secondary electron, you can get morphology. So you can use SEM to understand the morphology and also to understand what kind of composition or the elements are present in the film. Okay. So I did SEM to understand the morphology and also the grain structure. We can see the film is completely continuous film, and the grains are the morphology is actually very large size. So further I did AFM. AFM is nothing but atomic force microscopy. Here you have a cantilever. This cantilever oscillate with certain frequency. Okay, so this oscillated cantilever will interact with the sample surface, and it will deflect because of the forces, the van der Waals forces. It will interact with the sample surface, and it will deflect. So the deflected one is actually reflecting the surface. So the deflected one will be detected by the detector. So that is atomic force microscopy. So which also you can use to understand the morphology and also the roughness. In case of SEM, you can't understand the roughness, but in case of AFM, you can understand what is the roughness of the film as well. Okay, so I did both SEM and AFM to understand the grain size and the roughness of the films. We have large grain size around 100 nanometers, and the films are actually a bit rough, around 8 nanometers of rough in size. So next I did TM analysis on the interface between the semiconductor and electrolyte to understand how good is the interface. Does anyone know what is TM? What is TM? Anyone know what is the abbreviation? TM, you know, TEM.
Transmission electron microscopy.
Yes, true. It is transmission electron microscopy. Correct. What is the principle? And what kind of information can we get? So it is similar to your SEM. Go ahead.
Higher resolution than
Yes.
SEM.
Yeah, it is having much higher resolution compared to SEM. So you can get atomic level information.
Even dislocations can be seen through.
Yes, you can see the dislocations, you can see the various defects, you can see precipitates, you can see the crystalline structure. Yes. Yeah. So how it works is, again, you can have either in this case mostly field emission gun. So here you can generate the electrons from the field emission gun. These electrons have to be traveled through the sample. The sample has to be very thin, less than 100 nanometers in thickness. So when the samples are traveled through such a thick, very thin material, they will again interact with the material and carry the information about the material's structure. Okay, again through the scattering concept. So I have used again TM to understand what is the information that we can get about the indium oxide film and also the interface. So what we can see here is that indium oxide having good crystalline in nature, and it is having very good interface with the electrolyte. So indium oxide itself is very rough film that we have seen in the AFM. The films are very rough, but actually we can get very smooth interface because the electrolyte is like water, right? It can flow on any surface and form nice interface with the semiconducting material. Why I'm talking about interface? Because the electrons have to be accumulated and they have to be transported from one electrode to the other electrode. So the interface scattering has to be minimal. So to reduce the interface scattering, we should have very smooth interface with the dielectric material. So that is the reason we should have a smooth interface, and we can have very good transport of charge carrier from one electrode to the other electrode. So now comes the.
So is there any relationship, is there any relationship between the coarse grain or fine grain with conductivity?
Yes, there is a relationship as well. In case of large grain size, your scattering points are actually very low. Okay, so what happens is the electron can move very easily from one electrode to other electrode, so that the conductivity is very high compared to nanocrystalline size materials. Nanocrystalline size materials, you can have large number of defects, and that can actually lead to scattering of electron. So the scattered electron cannot completely reach to the other electrode, so that will reduce the current.
Okay.
Okay. So yeah. Any other question? Okay. So now comes the, yeah. Sorry, did anyone ask? Okay, now comes the electrical characterization part. So the printed precursor-based transistors are characterized. So what we see here is, for example, that this is the current, this is the drain current, and this is the gate voltage, and the applied drain voltage is around 1 volt. So this is a green curve that is showing the transfer curve. So what we see here is the very low current when the transistor is completely in the off state. Okay, it is not in the it is in the non-conducting state. But when it started to switch on, you can see the current is increasing significantly from let's say 10 power minus 9 amperes close to towards 10 power minus 4, 10 power minus 3 amperes. So you can get around 1 milliampere current in case of electrolyte gated transistors. Also, you can see the threshold voltage is actually the positive threshold voltage. So these are called accumulation mode devices, and the leakage current is also very low. So you have to understand that the current that we get, the green curve that is showing, the current that we get should be higher. That is the drain current, and the gate current or the leakage current should be lower. And of course, you can have a accumulation mode device where the threshold voltage is positive. Threshold voltage is nothing but the voltage where the device started to switch on. Okay, so on-off ratio, if you take the on-off ratio, that means this is the off state and this is the on state. If you take the on-off ratio, you can have 10 power 5 to 10 power 7 orders of magnitude change in the current. So you can have such a huge current change if you make such kind of transistors. But if I measure the IV curves again in a different mode, so this is called actually the gate voltage sweep. This is called a drain voltage sweep. So here the drain voltage is actually sweep, and the gate voltage is actually fixed at particular voltage. So what we see here is again the drain current and the drain voltage and the gate voltage. So the current has to increase initially and it has to saturate, but this is actually decreasing. This is called negative differential resistance effect. So this is happening because if you remember in the XID pattern, I told you that we have a detrimental secondary phase at 300 degrees centigrade films. So that is called indium oxychloride. That is actually contributing to the charge trapping. Okay, that's why the current is actually reducing. If I characterize the 400 degrees centigrade annealed samples as well. So there we can see completely, nice graph in the first case. Also the IV curves, here we can see increase in the current and the saturation region. Okay, so this is the ideal behavior of a transistor. So this we can get because the indium oxide is now completely pure indium oxide, and the grain size is very large, and the interface scattering is also very low. So that is leading to the large current and also low scattering in the interface. So if I measure the field effect mobility or calculate the field effect mobility, field effect mobility is nothing but how quickly you can transport the electron from one electrode to other electrode. So that is around 126 centimeters square per volt second for 400 degrees centigrade annealed samples. Whereas in case of 68, the current is actually, the mobility is actually very low, around 68 millivolts per decade. It's electronic devices. Okay, so that is the conclusion from this one. So not only the transistors, I also made the simple logic gate. CMOS inverter. CMOS inverter is nothing but you can have a combination of PMOS and NMOS. So PMOS is nothing but P-type semiconductor based transistor. These N-type semiconductor based transistors, where you can have combination of these two with the input, output voltage and also drive voltage. So what happens is when you apply a input voltage, let's say high input voltage, your output voltage will be low, or the output current will be low, and vice versa. So that is called the CMOS inverter. So here is the schematic that shows the, let's say, copper oxide P-type semiconductor and indium oxide N-type semiconductor, where we can have again the input voltage here, output voltage, and then you can have electrolyte, which is forming the capacitor with the both P-type semiconductor and N-type semiconductor. If I compare the CMOS inverter graph, what we have here is the output voltage graph and the input voltage. So we can see when the input voltage is actually very low. So this is less than 0. But the output voltage is very high. This is 1 volt in case of 1 volt of drain voltage, and 1.5 volt in case of 1.5 volt of drain voltage. So you can get high output for a low input. Okay, so we are inverting the signal. So just understand again, we are inverting the signal. For a low input, you get the high output, and then you have a transition region. After that, you can have high, low output for a high input. So this is called not logic gate. If anyone is working on transistors or anyone is working reading about logic gates, they know about not logic gate. Okay, so not logic gate you can have 1 0 0 1, right? So for a low input, that means for a 0 you can have high output, that is 1. Okay, similarly for a high input this is 1 and the output will be lower, that is 0. Okay, so that way we can create the logic gate using this printed electronics concept. So next I will talk about printed nanoparticulate transistors. So nanoparticulate, I have already mentioned before that you have nanoparticles which are, let's say, printed, but these nanoparticles have surfactants. So these surfactants we have to remove, right? How to remove the surfactant? We can do either UV light curing or laser light curing. So I did both. So to remove the surfactant, after doing the UV light curing, we can see the transistor performance is giving again very good compared to without curing. These are around 8 centimeters per volt second. The figure of merit of transistor, that is the field effect mobility, is higher compared to non-cured devices. Whereas in case of UV laser curing, here the laser curing is actually very efficient in removing the surfactant. So the mobility is now much higher, around 12 centimeters per volt second. So if I compare without curing, I mean, if I don't do any photonic curing, the mobility value is very low. But if I do photonic curing, the mobility is actually increased by more than 12 times because it is removing the surfactant between the particles and enhancing the electrical device performance. So far, any questions are there on printed transistors?
No, sir.
Okay. So next one is organic FETs and for gas sensing applications. Organic FETs are nothing but you can have an organic semiconductor. So again, you can have similar transistor structure, but on the top we replace the oxide semiconductor with organic semiconductor. Okay, organic semiconductors are very conducting in nature, and they're also sensible to different gas molecules. So here I have used organic semiconductor for gas sensing applications. So for organic sensing, I have, for example, ethanol. Ethanol is having very high volatile in nature, and also it can have interactive reactions with different organic semiconductors. Why I have used ethanol? Because ethanol is present in our human body, and also, of course, you can also have breath analysis when somebody is drunk or not, right? So also environmental monitoring you can have. So this kind of monitoring you need to have. So sensors we made using organic field effect transistors and detected ethanol. Ethanol is having the sensitivity towards the organic semiconductors. So here the percentage response versus time, and the minimum detection level is 600 parts per million. So again, what you see here is the response. Response is nothing but change in the current. So when I apply, let's say, air, so there is no response, but when you expose to ethanol molecule, there is response. So after some point, let's say if I close the ethanol molecule valve and expose to air, it comes back to the baseline. So we can see if we increase the concentration, we can increase the response of sensors. Okay, so that way we can create alcohol-based sensors, and also you can measure different alcohols, not only just ethanol. You can also measure octanol. Octanol is having, let's say, longer chain alkyl molecules, so that also we can detect. In this case, the detection level is 3 parts per million. So imagine such a low or such a high detection level is very useful for several applications. So not only that, I also detected different other molecules, octanol, butanol, ethanol, and methanol. So if I compare these responses, so we can see the trend actually. This is the methanol. This is actually shorter alkyl chain. Then we can have butanol. Then we can have, of course, this methanol and butanol. Then we can have octanol. So the percentage response is now increasing, although for octanol concentration is very low level. Okay, so we can have a high sensitivity when you increase the alkyl chain. That means octanol is having higher response compared to lower alkyl chain, for example, methanol or ethanol. So if I compare what could be the reason? So we can see something called hydrophobic and hydrophilic interactions. Okay, hydrophilic is nothing but water loving molecules. Hydrophobic is nothing but water hate. It doesn't interact with the water molecule. So that is the concept of hydrophilic and hydrophobic. So the organic semiconductor is actually hydrophobic in nature. So that's why it is interacting better with the octanol compared to methanol or butanol. So not only that, I also detected ketones. Ketones is nothing but, again, you can have 2-octanone, also butanone, and acetone. So all these three molecules as well detected using this organic device concept. So I also detected esters. Esters is actually released from fruits. For example, if you take strawberry fruit, you can have esters. So these esters are actually giving the smell. So it is important to identify the esters so that we can detect whether the fruit is fresh or it is spoiled. And if you want to have a sensor for the food spoilage or for the smart packaging sensor. So esters also I could detect using these organic sensors. Again, we can see isoamyl acetate, butyl and ethyl estates. All these three molecules as well can be detected using this organic device concept. So another one is I also worked on the plastic compete project. In case of plastic compete, the concept is to detect the odor coming out of the human body. Okay, for that also I used organic transistors. So because human body consists of very smelly fatty acid compound. Okay, these fatty acids have to be detected using organic sensors. So I detected 3 different analyte molecules. So all these sensors can detect all the 3 analyte molecules. But if I compare the responses of these analyte molecules, if you can see the percentage response versus concentration. So if I take 2 different sensors, you can have different responses. Okay, for in case of analyte 1. In case of analyte 2, there is not much response. But in case of analyte 3, there is again difference in the response. Why I am talking about difference in the response? Because you need to have both sensitivity and selectivity. Because there are different analyte molecules coming out of different human body, right? So I might have different analyte molecule and somebody can have different analyte molecule. So to distinguish whether the body smell is good or bad, or whether he is healthy or unhealthy, you need to identify different analyte molecules. So that's why we have to make different sensors that can detect different analyte molecules. So I made 2 different sensors, and these sensors have different sensitivity towards different analyte molecules. So we can test the body odor as well. So low body odor and high body odor. Low body odor, I mean to say, the smell is very small or very low, not unpleasant. Whereas in case of high body odor, the smell is very unpleasant. Okay, so we can see the response is different. In case of low body odor, the response is very low, around 20-25%. But in case of high body odor, we can get higher responses, around 35 to 45% of response. So such a difference in the response will give you distinguishing nature or the selectivity of different body odor as well. So just to summarize my talk, so I introduced the concept of transistors and also discussed the concept of printing, how we can use for, let's say, printing different materials, and also to make different devices. In case in this work, I made transistors. So in case of precursor-based transistors, I have used both high temperature-based both high temperature based precursors which are annealed at 300 degrees centigrade and 400 degrees centigrade, where we can get higher performances. And also I used nanoparticulate transistors and also a photonic curing technique to prepare both logic gates and also transistors at room temperatures on flexible plastic substrate. And the last one is I also demonstrated organic transistors for gas sensing applications. So with this, I would like to thank all my groups at Germany, and also my previous groups at Manchester and also Southampton. And I would like to thank the funding agencies, and I would like to thank all of you for your attention. I'm done with talk. If you have any questions, we can discuss.
Participants, if you have any queries, you can just unmute yourself and ask that question directly to the speaker. Meanwhile, there was a question in the chat box. Like, sharing of charging in Android phones, is it possible or not? If yes, how? If not, then can it be taken as a project?
Sharing of charging.
Yes.
Okay. Here in case of Android mobiles or even any mobile you take, what you have is battery. Okay, a battery is the one where you convert the electrochemical reaction into electrical energy. The chemical reaction is converted into electrical energy. Okay, so you store the energy in case of battery, which you can discharge and charge it. Understand? So the batteries are used in Android mobiles, which can be charged and discharged, which are having multiple number of cycles, and the battery materials are currently lithium ion batteries, which are used widely. So of course you can take battery project, and which can be printed as well. So the concept here is different from the transistor. It is not a transistor, it is a battery, which is used in mobile phones or any other, even laptops, you need the battery.
Sir, talking about batteries, sir, sir, in nowadays we have
I couldn't hear the question. Your voice is breaking. Mahesh, can you hear?
No.
Maybe you can type in the chat. You can type in the chat box. Mahesh can read out.
Yeah, meanwhile, if anybody else is having a doubt, you can just ask it. Okay, there is a question.
Yeah.
Can we replace the lithium ion battery with any other so that we can have sharing of charging between Android phones?
I think the question itself is not very clear. Sharing of charging, as I mentioned before, there the charging concept is different. Charging, I mean, you are fully charging the battery and discharging the battery. Of course, you can replace the lithium-ion battery with the latest available sodium-ion and also magnesium-ion, also aluminum-ion batteries. So people are working on alternative materials as well, because lithium-ion is actually is not very abundant. It's not very abundant in the earth crust. So people are working on alternative sodium-ion batteries. In the future, we may see probably sodium-ion batteries as well. You can, of course, take the project on batteries. Different battery projects are there: lithium ion battery, sodium ion, aluminum ion, fluoride ion battery.
Any other questions? You can unmute yourself and directly ask, but if you have a network issue or any other issue, you can always type in the chat box. Yeah. What is the role of metallurgists in this field?
Very good question. I myself is actually a metallurgist. I did my BTech in metallurgy, MTech also in metallurgy department. The role is actually the materials part, because as I'm talking about, you see semiconductor material, you see dielectric materials, you see conducting materials. So we can have invention in case of semiconductors, we can have invention in case of dielectrics, and we can measure different electrical properties of devices. So our role is to work on the material aspect so that we can improve the device performance and we can create new electronic devices. And processing as well. You can also work on the process concept. Different process can be used to make transistors or electronic devices.
Okay, one more question. Like, sir, if we use the wireless charging concept in Android phones to share the charging, will it work?
Wireless charging, I'm not sure about that concept. But of course, there are people who are working on wireless devices. Earlier, you have headphone with wires, right? Nowadays, you have wireless headphone. So people are working on wireless concepts as well. Perhaps in the future, we might see this wireless device concept where you can also share the charging. So it may be possible in the future. As of now, I'm not sure.
Any more questions? Okay, I think. Okay, there is one more question.
Huh.
As per my knowledge, metallurgists in India are more towards conventional metallurgy process like iron making and
Yeah,
steel making.
yeah.
How should one make career in this field?
Definitely, you can have a career. You can see me as a live example, right? So the material science and metallurgy part is evolving. So if you see, for example, 1970s, people were completely working on iron and steel, right? Later, people started to work on composite materials, ceramic materials, and also batteries, energy materials. And people are now working on highly advanced topics, nanotechnology, advanced topics like as I'm doing electronic materials, sensors. You can have even quantum devices. So definitely there is career because the field itself is evolving and very broad. So you can see the department name, for example, in case of IIT Hyderabad, it is metallurgical engineering and material science. So that means both core metallurgy and advanced topics of material science are required for the future. In fact, it is advantageous because if many people are working on the same concept, you can have significant competition. But if you are unique in a field, you can imagine your opportunities are actually very high. You can get a job or anything very easily. So go for something unique and go for something advanced topic so that you can have a good career.
Okay, so thank you, Dr. Suresh, for your valuable time and a very informative session, which was very much benefiting the students as well as the participants who are attending this session. They are very grateful to you for the very nice session. And on behalf of RGUKT-Basar, I'm very thankful for thankful to you for accepting our invitation and spending your valuable time in sharing the knowledge to the participants. Thank you, sir. Thank you for your valuable time.
Thank you, Mahesh. Thank you for giving me this opportunity again, and thank you all of you, all students, for attending the talk. Thank you, and hope to see you again at some point in the future.
Okay.
Okay, then I will leave.
Yeah, sure. Thank you.
Thank you.
And I request Mrs. Anupama Sridevi, Head of the Department Mechanical Engineering, to kindly address the gathering.
Should I leave? Should I stay?
Yeah, you can stay just a minute. It's a valedictory session, so just.
Thank you, sir. I congratulate all the participants on successful completion of this 1 week STC on emerging technologies in processing of advanced materials and its characterization. I also congratulate the organizers for their continuous efforts in making this STC possible, and also thank all the resource persons for sharing their valuable information through this. And I also looking forward to conduct such programs further with all your support. And I once again thank all the one who has supported this event, sir. Thank you, sir.
Thank you, ma'am. This is information to all the participants that your e-certificates will be posted to you through for whatever email ID that you have given to us in a couple of days. And the feedback link is also been given in the chat box, which you can fill it. And I finally conclude the short-term course by vote of thanks. Now, it's been a great pleasure to organize a short-term course on emerging technologies in processing of advanced materials and its characterization. I'm extremely grateful to Mr. Rahul Bojja, IAS, Honorable Vice Chancellor, and to Dr. Y. Rajeshwar Rao Garu, Administrative Officer, for his support in providing the due approvals on time for smooth conduct of the event. I convey my sincere thanks to Professor S. Rajesham, Mr. Shekhar Sheelam, Associate Dean Engineering, Dr. G. Devaraju, Associate Dean Sciences and Humanities, Mrs. Anupama Sridevi, HOD, Department of Mechanical Engineering, for their continuous support and advices, which had been greatly helped in organizing the program in a structured manner. I'm very grateful to all the resource persons for gracefully accepting the invitation and confirming their willingness to share the knowledge in a very short period of time. In spite of all the odds, their prior commitments, and their busy schedule, the resource persons have put their complete effort in justifying their role in sharing the knowledge to the participants. in the upcoming technologies. I'm really indebted to each one of them who have accepted the invitation on a goodwill basis. I take this opportunity to express my sincere thanks to all the department faculty members and to Mr. Srinivaslu, System Administrator, for their constant helping hand in most of the aspects throughout the event. I acknowledge the unwavering support received from the department lab staff members and the university administration for providing all the possible logistic support to organize the event. And at last, but not the least, my sincere thanks to my organizing team comprising of Mr. Narendra and the students from pre-final and final year for their efforts in designing the brochures, certificates, etc. and for handling all the technical issues. I once again thank everyone whose contribution has made this event a successful one. Thank you one and all. So here comes the end of the short-term course organized by the Department of Mechanical Engineering, RGUKT-Basar. Thank you all for your participation. Thank you, participants. If you have any doubts,
Welcome, sir.
you can just unmute yourself and you can ask me directly. All the certificates will be posted by Wednesday next week. Next week, Wednesday, okay?
Thank you, sir.
Thank you one and all.
Thank you, sir.